Hi guys, in this video I'm going to explain you about the sensitivity analysis question in linear programming. So first of all, we'll see what is this question. In sensitivity analysis, we see how sensitivity, the optimal solution to the changes in data values, derive the optimal solution to the below question using graphical method. Maximum 5x1 plus 7x2, that is the question. Yeah, you want to have a maximization here. So this is a maximization question. Max 5x1 plus 7x2, and these are the given constraints: x1 less than or equal 6. I will put those things down. X1 less than or equals 6, and this one is the second constraint: 2x1 plus 3x2 less than or equal to 19, and the third one is x1 plus x2 less than or equal to 8. And these are the non-negative what we call variables. Okay, what happened? What hasn't? Right, I will put like this way. Right, x1 comma x2 greater than or equal to 0. Okay, assume the first part of that one, assuming the coefficient of x1 and x2 in the objective functions are c1 and c2 respectively. Find the value range of c1 and c2 where current optimal solution would not change. Okay, that means you want to find out the values for the c1 and c2. That means c1 and c2 are the coefficient of your maximization function. That means your object function. And you want to find out the value, the range of values for those constants. That means now here you know that this is our objective function. This one, the 5x1 plus 7x2. Okay, we can take it as 5x1 plus 7x2 equals something called z. Okay, so then you can see what is the x1. X1's constant, the coefficient value of the x1 is 5, and the coefficient value of the x2 is 7. And this thing you can take it as the intercept. Okay, this is a linear function. Okay, 5x1 plus 7x2 equals z. Okay, how do we get the gradient of linear equation? You can easily get, first of all, you have to determine, you have to what we call the, you have to finalize what are your independent variables and the dependent variable. Okay, normally it will be easy for me to get x1 as the independent variable. That means the variable which is on the x-axis, and the variable which is on the y-axis, that is called the dependent variable. I will take it as x2, but you can take any of your choice. Okay, so according to that, since x1 is my independent variable, this is the m value, the gradient. Okay, gradient, but the coefficient of the x value, it is not the gradient. But since this is our dependent variable, you have to divide it by this coefficient value. Okay, then only it will be becoming as y equals mx plus c. Okay, so the gradient of this one is this coefficient divided by this one. Okay, it will be easy me to explain by my the handwritten note. Okay, see this one. Now according to our objective function, this is our objective function, z equals 5x1 plus 7x2. Okay, according to this thing, if you convert this thing as y equals mx plus c, okay, this I told that this x2 will be my y. If it goes to the other side, the gradient of this function will be minus 5 divided by 7. Okay, the objective slope should be in between the value of your the lines. Okay, so therefore they will ask us to get the range of the values. So I know if I take this function, I can first keep one thing as a constant. Okay, and substitute the other one as the value that they have given. So for this x1's constant coefficient, they have given it as c1, and I will keep this 7 as it is. So therefore the slope of this function, then the function becomes like this: z equals c1 x1 plus 7 x2. Therefore slope of this one will be minus c1 divided by 7. So the range will be in between this range, because those are the ranges of the straight lines, the boundary constraints that they have given. Okay, the boundary lines, if I take the question like this way, if you take this equation, what is the gradient or the slope of this one? The coefficient of the x is the 2 and the y is 3. Therefore this becomes minus 2 over 3, and this becomes minus 1 divided by 1, because the coefficient of this x2 also 1. Therefore the range will be in between minus 2 over 3 and the minus 1. Okay, again I will go to this one. So you can keep it like this way: minus 1 less than or equals minus c1 divided by 7 less than or equals minus 2 over 3. Like that way, after that you have to simplify. Okay, by multiplying this by 7 both sides. Okay, you can take minus 7 less than or equal minus c1. After that you have to remove the negativity. You can multiply by the negative, then this inequality will be opposite. So 7 greater than or equal to c1, like that, greater than or equal to 4 divided by 3. After that you can keep it like the other way around if you want, or you can keep like this way, then the answer will be like this way. Similarly, you can find out the other constant, that is c2, but what you want to do, you want to keep this 5 as the constant, and you want to keep this c2 as the coefficient of the x2. Okay, the same manner, then what will be the slope always the negative value of the independent coefficient. So this will be minus 5 and divide by c2, minus 5 divided by c2. Okay, after that you have to keep those things to the given range. Range means the slope of those two straight lines, boundary constraints. Then this thing we have taken as minus 5 divided by c2. After that you have to interchange the things, and since it is in the denominator, c2 is in the denominator, you have to get the reciprocal of the values. How do you get the reciprocal of the values? When you are getting the reciprocal, always the inequality will be changed. Then minus 1 greater than or equal minus c2, it goes up, c2 divided by 5, and greater than or equal to minus 3 over 2. After that you can make multiply by this 5, and you can take the answer like this way. But since this is minus, always, so you have to multiply by the negative values, then you are getting the answer like this way. I think you got that point. Again, we'll back to our presentation, because it will be the some part of the presentations it is not visualized clearly. That's why I am going to my handwritten document. Okay, then after getting those coefficients, they are asking about the terms. What do you mean by the shadow price and the binding constraints? Constraints and the shadow price. Okay. The definition of the binding constraints. The binding constraints are, you can easily consider the binding constraints as the those are the points which belongs to the optimal solution. That means now your constraint lines, those are getting intersect at one position. Okay, we are calling it as the optimal solution. So the binding constraints are those which intersect to form the optimal solution. That is the easiest way of explaining about the binding constraint. Binding constraints are those which intersect to form the optimal solutions. Now here we know that we have two binary constraints. One is 2x1 plus 3x2 less than or equal to 19, and the other one is x1 plus x2 less than or equal to 8. Okay, so those two are getting intersected, and then we are getting the value of the optimal solution. Okay, for the binding constraints, the RS side, okay, right hand side always equals to the left hand side, and that is the we are identifying a binding constraint by that result. Always, if it is a binding constraint, right hand side, the right hand side value should always equal to the left hand side at the optimal solution. At the optimal solution, always left hand side and the right hand side equals. Okay, then what do you mean by the shadow price? uh, okay, we know that in the shadow price we are increasing the right hand side by a 1 unit. Okay, it is not always should be a 1 unit, but we are normally increasing it by 1. Okay, the shadow price is a marginal change in objective function per unit change in the constraint right hand side. Okay, that's the way we are defining. The shadow price is a marginal change in objective function per unit change in the constraint right hand side. The shadow price is non-zero for the binding constraints and 0 for the non-binding constraints. What is it? This shadow price is non-zero for the binding constraints and 0 for the non-binding constraints. Right, then we'll move to the third part. What they have asked in the third part. Okay, I didn't explain the graph there. Okay, this is the graph that I have drawn by a graphical tool, but you want to draw it by your, I think you want to draw by the handwritten way, like the way I have drawn here. Okay, you want to have a handwritten like this way, you want to draw the graphs. Okay, this is the first graph that I've drawn, but it will be easy to me to explain using the graphical tool thing. Okay, I will explain where the position the what we optimal solution exists. Okay, these are the two constraints. 2x1 plus 3x2 less than or equal to 19, that is the binding constraint, and x1 plus x2 less than or equal to 8, that is also binding constraint, and this one is also a constraint, but it is not a binding constraint, x1 less than or equal to 6. I will later tell how this becomes a binding, this is not a binding constraint, and how these two are becoming a binding constraint. Okay, in order to find out the optimal solution, we are always taking the isoprofit line. This isoprofit line also called as a contour line. Okay, contour line. That means we are drawing a line which has the same slope as the your objective function. Okay, after that, if it is a maximization problem, if it is a maximization problem, you are finding out the last position where it leaves the feasible region. Now this is our feasible region. Okay, and this is the, now when we are drawing this type of isoprofit line and check whether what is the last position that it leaves this feasible region. Now we have identified it as this 5,3 position where these two binding constraints are intersected. So that will be our optimal solution. Okay, then right after that, now we want to find out this the binding constraints, the value of the shadow prices. Now this x1 less than or equal to 6. Okay, x1 less than or equal to 6 means it does not have the proper binding. Okay, because it does not have what we call upper limit. Therefore, if it does not have an upper limit, its shadow price always becomes 0. Okay, always if you want to find out the shadow price, it should be bounded. Okay, if it is not bound, okay, the shadow price always will be 0. Then for the next line, okay, next line, the next constraint line, 2x plus 2x1 plus 3x2 less than or equal to 19. Okay, now we are going to change the right hand side by 1. If you change the right hand side by 1, this 19 becomes 20. From 19 to 20, find the intersecting point. Okay, intersecting point again with x1 plus x2. Now we are not changing the other constraint line. Okay, you can't change the other constraint line, only you want to change this one by 1. Okay, this becomes 20, and after that simplify these two by using the simultaneous equations. If you simplify that one, you're getting the answer for x1 and x2. Okay, after that one, substitute that those answers to your objective function. Okay, here we have got the answers as x1 equals 4 and x2 also 4. Okay, if you substitute it to the objective function, we are getting the answer as 48. That is a new maximization value. Okay, the earlier value, the original value was 46. Now, so you want to get the difference of that one, 48 minus 46. That value is called as the shadow price. What you want to do, you want to increase the constraint line by 1 and consider it with the other constraint line and simplify and get the values for x1 and x2. After that, substitute those values to the your objective function and get the new maximization value. Okay, then compare that value with your original objective value. Then that difference is called as the shadow price. The same manner you can increase this one, x1 plus x2 equals to 8. It will be increased by 1 and it becomes 9, and after that you can simplify it with the 2x1 plus 3x2 equals to 19. Okay, and get those values, and the same manner you can get the difference of new maximization value and the old maximization value, and that is called as the what we call the shadow price. Okay, it is the shadow price. Also it is written like this way: 2x plus 1 2x1 plus 3x2 equals to 19, and x1 plus x2 equals to 7. If it is I think is that correct? I think I have done a mistake. Yeah, right. I will show it from here. Now x1 yes, x1 plus x2, you are increasing it by 1. Okay, but yeah, if you yeah, you can do it by not only by increasing, you can do the same thing by decreasing as well. Okay, the answer won't change. That's way I have done in the presentation. We can go like that way also. X1 plus x2 equals to 9. 2x1 plus 3x2 equals to 19. Now this is the normal way in the several websites have explained, by increasing value, increase in the value, but also we can do it by the decreasing. So you're getting the answers as x2 equals 1 and x1 equals 8. Okay, then you are getting the answer for the new maximization value as 47. So the shadow price is z new minus z old is the equals, it is equals 1. Okay, right. Okay, then this will be the problem. Okay, many guys asked this question. Okay, I also have taken so much time to understand this problem. This is the fourth part of this one. This is a question. Now we'll see the question first. The fourth part of this one. Calculate the range of applicability for the above calculated shadow price. That means in the easiest way, what they have asked, they are asking the range of feasibility. Range of feasibility. range of feasibility also it can be considered as the range of feasibility or the applicable range of applicability. But the problem is now we are going to get this thing by the graphical method. It will be somewhat difficult to understand when you are considering it with the graphical method. Okay, but it is, if it is in the simplex method, it will be easy to understand. So this thing I also have taken long time and understood this one. Okay, that's why I have created this video in order to explain the things what I have understood there. Right. Okay. We'll slowly understand this one. For the constraint line, 2x1 plus 3x2 less than or equal to 90. Then we'll first consider this one. Okay. There you want to find out upper and lower limits. Okay. How do you find the upper and lower limit? Now this orange line is my 2x1 plus 3x2 less than or equal to 90. This is that line. Okay, constraint line. Okay, this gray line, this is what x1 plus x2 less than or equal to 8. This is our x1 less than or equal to 6. Okay, right. There will be what we call the optimal value. That is the intersection between those two constraint lines. Okay, then after that you find out now the what we call the range of feasibility. How do you get the range of feasibility? You have to consider now if there are two constraint lines. Okay, you want to consider one constraint line and their upper limit and the lower limit. Okay, this thing like this. Now I'm considering about the 2x1 plus 3x2 less than or equal to 90. Then consider about the other constraint line. What is that one? X1 plus x2 less than or equal to 8. There we try to find out the place where it is getting intersected with the y-axis. It is this position. Okay, that is the upper position. Okay, find out the coordinates of that one. That is 0, 8. Okay, and after that it is going and you can't take this part because after that by this x1 less than or equal to 6 line it is getting bounded. Okay, because there is no range of here. Okay, you are getting the feasibility from this place. Okay, then find out the place where you are getting intersected with that line, that boundary line. Okay, then what do you want to do? You want to draw parallel line with the slope of your objective function from this place. That is the one place. Okay, this is the first place, that is upper limit, and the lower limit you are getting by this what we call the unbounded line. Okay, x1 less than or equal to 6. Okay, from those two places draw parallel line to the slope of the objective functions. We know it is like -5 divided by 7, -5 divided by 7. If you draw parallel lines, it will go like this way. So this is the upper limit and this is the lower limit, and you can get the range from that one. Okay, so how do you get the range? Okay, and we know that our line is 2x plus 3x. Okay, 2x plus 3x, 2x plus 3x. Okay, take the coordinates of the upper limit. It is 0, 8. Okay, and lower is what? 6, 2. That is, you have to find out by the graph. Okay, where it is getting intersected. Okay, then substitute those values. Where this one. Okay, substitute those values. Then 2x is if you want to take the upper limit, 0 and 8. X is the 0 and y where coordinate is 8. You are getting the value as 24. And the lower limit is since this is 6 and 2, you substitute those things to 6 plus 3 8, you are getting the value as 18. So then you can take it as this way. Okay, this is the representation of the closed boundaries. Okay, then this value lower is 18 and upper is 24. You can represent it like this way. Okay, so the shadow price range is 18, 24. Shadow price range, another name is that range of feasibility. Okay, the same manner you can do it for the what we call the next constraint line. Now what do? You have understood what you want to do. Consider the other constraint line. Now what is the other constraint line? Means 2x plus 3x, that line. Okay, 2x plus 3x less than or equal 9. And this is representative what we call orange. Okay, then what you want to do, you are finding out the place where it is getting intersected at the y and also in the unbounded line. Okay, from those two positions, what you are going to do, you are going to make parallel lines with the slope of your objective function. Okay, objective function. Okay, and find out what are the places it is getting intersected. Now this is getting intersected here. Okay, this place. Okay, that is 0 comma 1903, and this is okay, this upper limit. Okay, upper limit, why we are calling it as the upper limit? Because it is going up. Okay, then this one is getting intersected here. Okay, and find out the places where it is in the feasible region. Okay, you can't take like this path because it is not in the feasible region. This is the point where it is in the feasible region. So this is 6 comma 7 over 3, and this is 0 comma 9 over 19 over 3. After that, the same manner you can take the upper limit by considering the upper coordinates, substitute it for the your what we call line coordinates. This is constraint line is x1 plus x2. So these upper values will be the lower values will be x1 is 6, y is 7 over 3. Then x1 plus x2 is 6 plus 7 over 3. You are getting the value as 25 over 3. And also by substituting the values for the other thing, you are getting this part 0 comma 19 over 3. You can get the value of the lower limit by that way, 19 over 3. So 19 over 3 and 25 over 3 are the what we call upper and lower limits. Okay, I think you understood those things. And the next constraint line, okay, that is x1 less than or equal to 6. We know that it is unbounded. Because of that, it does not have a upper limit. Okay, it only consists of a lower limit. How do you find out the lower limit? That is the place where it is getting intersected with those two constraint lines. Okay, you want to only consider about the other two constraint lines where it is getting intersected. Okay, that coordinate you can consider as your the point of intersection. Okay, then since it is not a binding constraints, no upper limit. Okay, the lower limit value is only it is 5. Okay, so lower limit, since the lower limit is 5, the upper limit is considered as infinity. Okay, so you want to put what we call just bracket. Okay, because infinity is unbounded, therefore you have to keep like this way. Okay, those are the things what you want to understand. I think I will post industry related things in my YouTube channel. Okay, I think it's better to subscribe those things. Okay, thank you very much.